Okay, so let's talk about parameter estimation. So in this section of chapter 6, parameter estimation, we're really looking at how to find the mean. For example, if you're if a factory making products and you have an assembly line running and you want to know the average weight of all of the products. So we're talking about the population mean. And the problem is usually you only can take a sample of the population. So we're trying to estimate the population mean based on the sample mean is our goal. So remember, mu is the population mean and x bar is the sample mean. And what we really like is an expression like this one where we know that the population mean is the sample mean, which is what we can measure. We take some samples, we take the average, and we'd like to know plus or minus what delta with some confidence level. So I wanted to point out one thing about this confidence interval and the confidence level. As you get more confident, higher level of confidence, 99% versus 95, the delta gets bigger, because if you're going to be 99% confident, you have to make the thing big enough to have 99% of the occurrences. If you're okay with 80% confidence, then your delta can be smaller because it only has to work 80% of the time. So there's a different correlation between increasing the confidence. Higher confidence means larger uncertainty here. Confidence comes up in this part of the chapter, and it's used for a couple of different terms. So don't just say confidence and sort of read ahead when you see that word confidence. So we're looking at x bar plus or minus delta with 95% confidence. Delta here, this is the confidence interval, and it's got units the same as your measurement. So if you're measuring in grams, it's in grams, centimeters, it's in centimeters. Confidence level is the probability, so 95% confidence level is what we're talking about. So interval versus level sound very similar, but they're very different terms. And then just to confuse things further, when we talk about the confidence level, sometimes we give that in terms of alpha, which is the level of significance, and it's 1 minus the confidence level. So confidence level doesn't have a symbol, so I usually use CL for the abbreviation. Alpha comes up in a lot of equations, and it's 1 minus the confidence level. So a confidence level of 95%, same as alpha level of significance of 0.05. So this estimate that we want of the accuracy of our mean or our average comes from the central limit theorem. And so it's used for a lot of things in the statistics, and it predicts the distribution of a population based on the distribution of a sample. So you can use it for predicting the accuracy of estimations, like we're going to use it here. And so the setup for our use of the central limit theorem is we're going to take n samples, say 10 samples off of our assembly line, and calculate the average weight, maybe x bar. Then we take another n samples and calculate another mean, this second mean. So we got the first set of 10 samples and took their average, another 10 average, keep going, more averages and more averages. And what we get is we get a sample of sample means. So from each set of data we get one mean value, and so we get a set of means. So the central limit theorem, what it says is if n, which is the number of samples you took, so the number of things off the assembly line, is large enough, and here large enough will always mean greater than 30, 31 or more. With that size n, then the central limit theorem says that the means of all of your samples have a normal distribution. So the distribution of the means is a normal Gaussian distribution, and we can find the standard deviation of the distribution of the means, sigma x bar here, and write it in terms of the standard deviation of the population, sigma, divided by the square root of n, where n is the number of samples. Again, has to be greater than 30. So this is the central limit theorem, its equation. And here are the terms again. So the standard deviation of our means, also called the standard deviation of the mean or the standard error of the mean. Sigma is the standard deviation of the population, and normally we can't measure the whole population, so we often turn this around to find things like population, things that we need. So this is useful for finding population standard deviation based on a set of samples, distributions in samples, and it's useful to point out that this is true even if the original distribution is not a normal distribution, and because of this, things tend to become normal or Gaussian distributed, so that's why we use this distribution so often. Again, we're trying to find that delta, the confidence interval on the population mean. So what we start with is this distribution of the samples. So we took 10 samples and found the mean, took another 10 samples, found the mean, another 10 samples, found the mean, and now we have this distribution of means. If we kept taking samples forever and averaged all of those means, that would find the population mean because we would have sampled the entire population. So z equals 0 is the population mean. But every time we take 10 samples or whatever, we're somewhere on this curve. So here's a sample that I took 10 samples, I found the average, and this average is here. And so if we want to find the confidence level, what is the range of values of means that falls into the 95% probability? So remember, the area under this curve is the probability. So if our measurement is between here and here, and the area is 95%, then you have 95% probability that your measurement will fall between these upper and lower bounds. So the probability of an average of your samples being between negative z alpha over 2 and z alpha over 2 is the area under the curve. And we can find it from the table of normal distributions, which is just 1/2, one side. And so if we find the area from the table for that z alpha over 2, multiply it by 2, that should be the confidence level, again our 95%, or 1 minus alpha. So these equations are how we work this. Normally we start with a confidence level. We want 95% confidence. And we want to work our way back to z. So we find the confidence level. That gives us the area. The area in the table gives us z. Then we look at the definition of z. Z alpha over 2 is x bar. That's our measurement in this case because we have a set of averages, minus the population average, which is the center here, divided by the standard deviation of the means. And plus or minus here because this could be positive or negative, and it'll give the same area. So if we take this equation and solve for the thing that we want, the population mean, we get this equation here, x bar plus or minus sigma x bar times z. And then we use the central limit theorem to get rid of sigma x bar and write it in terms of the population standard deviation divided by the square root of n, central limit theorem. So this is the form of the equation that we wanted. We wanted the population mean is the sample mean plus or minus some confidence interval with a certain confidence level. So you'll have to think your way through this. The book does a nice description of it as well. It turns out that getting to the answers is pretty easy though. So here's the step-by-step process. So if we start with a confidence level, like 95%, and we take a sample of measurements, at least 31. From that sample we can calculate the sample mean x bar, and we can calculate the sample standard deviation s. There's an assumption in here that if n is greater than 30, then the sample standard deviation and the population standard deviation are close enough. So we equate them with each other here. So that's what we do with our sample. Then to find the confidence interval here, we we find the area, which is the confidence level divided by 2, because that's the area in the table. From that area, we use table 6.3 and find z alpha over 2. Once we know z alpha over 2, we already know the standard deviation from our sample. We know the number of samples we took, and that will give us the confidence interval, delta. So once we get delta, we can say that the population mean is the sample mean plus or minus delta with 95% confidence. Here's an example with some numbers. So a manufacturing site measures the size of 35 widgets, finds the average of the 35 widgets to be 3.9 centimeters, and the sample standard deviation was 0.07 centimeters. So then we're going to find the confidence interval of the mean with a confidence level of 95%. So the first step, given this 95%, we need to find the area, which is the confidence level divided by 2. So 0.95 divided by 2, 0.475. Then we look into the table. It's over here. This is the area. So area of 0.475 has a z value. It's in the 1.9 row, and it's in the 0.06 column. So 1.96 is z. Now we just plug it into the equation. So we have the standard deviation was given to us, n given to us, z we just got, and so we can find that the confidence interval 0.023 centimeters. So compared to 0.07 was the standard deviation. So it gets smaller because we're normally dividing by this n. So we can say that the population mean is 3.9 plus or minus 0.023 with 95% confidence level. 95% of the time that's true. Okay, so that's the first parameter. We're estimating this confidence interval, and we need n greater than 30. We use the normal distribution table to find z, and the rest of it comes from our measurements. So next time we will look at what happens if n is less than 30. We have a case for that too, and it's a table, as you might guess.